Looking at section 11.9 in Algebra 2, binomial distributions. So 11.9, binomial distributions. Okay, so binomial distributions have distinct properties, and they have many different applications that kind of go with this. One of the first ones we talk about is a binomial experiment. Okay, so a binomial experiment. Okay, in a binomial experiment, we have a couple things that happen. Number one, there is a fixed number of trials. Okay, for instance, we have 10 trials total, and we're doing the same thing repeatedly. So we're testing it again and again type thing. So 10 things there. In each trial, there are two outcomes. Okay, generally one in favor, one not in favor. A win, loss. Okay, happens, does not happen. Okay, we take a look at the extreme on here, not every little thing that could happen in here. For instance, you're going to pass this class or fail this class. Not that you're going to pass with an A or pass with not an A type thing. That's what we're talking about, these two outcomes in here. The trials are independent. Okay, independent. Okay, so there's no dependency on this. And then the probability of each outcome is constant. Okay, so the probability of outcome is constant. Okay, so once again, fixed number of trials, two outcomes with or without. Trials are independent of each other. And then we talk about the probability of an outcome is a constant, that all of a sudden, oh, the chance of you passing is 50%. Also, now the next time you take, chance of you passing is now 80%. Okay, so the outcome has to have some sort of a constant that goes with it. When we start looking at the probability of an event, then, once again, given this binomial experiment, we'll look at this formula. Okay, this formula, n minus x, talks about the combination of the total number of trials with the total number in favor to the probability of it happening to raise to that power, the probability of not happening raised to the difference of this. So this talks about n is our total trials, x is our favorable trials. Okay, basically the probability that we want. So if we have 10 trials and you want to win 5 times, or you want to win 6 times. So we would have 10 and then 6 here. So that means 6 would go here, 4 would go here. Once again, n minus x would be 4. So this n minus x would be the not there. Now the probability of you getting that favorable. So this is the probability of the event in favor. And then Q is a probability of not that event. Okay, so if there was a 70% chance that if you took a class 10 times, you're going to pass 6 times. So we'd have 10 times 6 times 0.7 right here, and then we would have 0.3 over here, because once again, either it happens or it does not happen. Altogether, both of those should add up to be 1. So that's why we look at the 0.7 and then 0.3, or whatever we're relating towards. So let's take a look at number 8. Okay, so on number 8 here, it says that x equals 3, n equals 8, and the probability is 0.3. It asks us to find the probability of x successes and n trials for the given probability of success p on each trial. So what we would do here is we would take 8 combination 3, and then we would take 0.3 to the third power, 0.7 then to the fifth power. Because once again, 8 minus 3 would be 5. These two have to add up to be this. this matches with this is here, then that's in the next one. Considering what's happening here, we then would type this into our calculator, and we would see that we'd have approximately 0.2541. So that would be our probability here. Now, how does this relate to an actual story problem? Let's look at number 12. Okay, so on number 12, we talk about battery life. So a calculator contains 4 batteries. With normal use, each battery has a 90% chance of lasting for 1 year. What is the probability that all 4 batteries will last 1 year? So we have 4 batteries, 90% chance that a battery lasts for 1 year, and we want all 4 to last. Okay? So once again, either they're going to last or they're not going to last. They're either going to keep going or they're going to die, those batteries. Okay, one or the other on here. So considering that we have 4 batteries, and we are considering that we want all 4 to last. Now, there is a 90% chance that all 4 will last. There is a 10% chance then, well, that 0 would last then. So if we consider what's happening here, we would type this into our calculator, and we would get 0.6561. Okay? Or if you are more comfortable with percents, if you start talking about this, basically there's a 65.61% chance that if you had 4 batteries in your calculator, once again talking about the big graphing calculators, have 4 AAA batteries, that it would last for a full year without having to change out those batteries in there. Once again, you're doing fairly well on this. Now the next part to this section, okay, that's the binomial experiment part. Once again, relating to what happens if we have different scenarios in there. We'll do one more. I just want to kind of work through the problems as we go. But the next part kind of discuss that binomial theorem. Okay, so if you remember way back, when we talked about a plus b to that nth power. Okay, so a plus b to that nth power. And we had to multiply it out all times. Well, we had Pascal's triangle that we would go down to give us the coefficients. I gave you a different technique where we took the coefficient times the power divided by the term number, had to keep going through. Well, now, here's the secret. Okay, here's how this gets easier. The binomial theorem. Okay, so the binomial theorem. The binomial theorem states that if we have a binomial raised to a power, the multiplication out on this power will be the combination of the power combination 0, and then we would take our first term to the nth power, our last term to the 0 power, plus then n combination 1. And then now we would have a to the n minus 1, b to the 1. Once again, remember this power went down by 1 as this one went up by 1. Plus, and then this would keep on going. We would get n combination n minus 1 to the a to the first power then, b to what would be that n minus 1 power, plus then, coming down here, n combination 0, or I'm sorry, n combination n, I can't have n combination there, it's here, n combination n I built all the way up. Now we'd have a to the 0, because n minus n would be 0, and then b then to that nth power. And this is what we would be looking for and going through. So here's what it all kind of boils down into. Let's look at number 16. Okay, on number 16 we talk about 4c minus d to the 4th power. Now, remember, we cannot just take this power and distribute it into here. We can't do that because that minus sign in there. This is a binomial, it's not a mono. There are no rules of exponents. This is 4c minus d times 4c minus d times 4c minus d times 4c minus d. So it's only a 4th power, not the worst, but this is what we would work with it. We would look at our theorem here. We would go 4 combination 0, and then we would go 4c to the 4th power, a negative d to the 0, because once again you have to remember this is 4c plus a negative d to the 4th. We got to have that sign accounted for somewhere. Then we would go plus, we would have 4 combination 1, and then now we would go 4c cubed first power, sorry, and then a negative d to that first power. Plus then 4 combination 2, now we have 4c squared and then a negative d squared. Plus then we would have 4 combination 3. So once again you see this number, this 4 combination 0, 1, 2, 3, 4 is going to be my next one in here. We have that 4c once again to the 4th to the 3rd squared down to that first power. As that next part ascends up, remember one descends down, one ascends up. So we have the 0, we have the 1, we have the 2. Now we're going to have that negative d to the 3 power. Plus then we would have 4 combination 4, which would be 4c to the 0 then, and then negative d to the 4th. Okay, and so this would be writing everything out. So remember in the past we had to write everything out, then we had to calculate what's going on. So some of the things that we started thinking about. 4 combination 0 is 1. Okay, so we talk about 4 combination 0 as being 1, and then times 4 to the 4th power. Once again, this right here is a 1 right here, so that kind of cancels off. So we would have a number of 256c to the 4th. Okay, so 256c to the 4th. Now we take 4 combination 1 times 4 cubed times negative 1 to the 1st, means that we would have a minus 256 c cubed d to the 1st power. So once again, remember we had to know what this coefficient was, multiply here, and then we had to distribute all this out. We had to figure out all this stuff. Well, here are our coefficients, and then we're just organizing our exponents so that we can easily multiply it out. So 4 combination 4, type in your calculator, times 4 cubed times negative 1 to the 1st. That gives me this number right here. Then I look at my variable, c cubed d to the 1st. Considering my next one, I would type in 4 combination 4. So once again, if you want to see what's going on here, I can do this one here for you. I would type in 4 combination 2, and then I would go times 4 squared times a negative 1 squared. Oh, common error. Well, if I'm squaring negative 1, it should be positive within here. So as we're thinking of this, we would get a positive 96. Okay, so now we go plus 96. Now we have c squared d squared. Then we would go to our next one. Once again, we come down here, 4 combination 3 times 4 to the 1st times a negative 1 cubed. Once again, most of it's typed in. We could just go back in and change our exponents, change that value right there if we wanted. I do have the answer worked out already. So this would be a minus 16 cd cubed. Once again, c to the 1st, d's cubed. Here, this part cancels because 4c to the 0, I have a monomial to 0 power, so that's going to be a 1. 4 combination 4 is also 1. So we see negative 1 to the 4th is there, so we just get plus then d to the 4th. Okay, and so this is our multiplied out power. So basically, rather than trying to figure out what all these coefficients are, the combination tells us those coefficients. Okay, so Pascal's triangle really is a combination rule of binomials. Now, what really helps with this, is the simple fact that on number 20, okay, number 20 says that, okay, let's say, I'm going to change this around a little bit so we can see a little more in depth. Let's say we had this problem, and I said, find the fifth term, okay? So I'm going to scribble off this number 20 because I really just modified this problem. If I said, let's find the fifth term, okay? So, in the past, we would have to figure out every single term up to that fifth term. The nice part about this binomial part as we start looking through this is we have combinations for all our lead ones, and then those exponents are kind of follow in a distinct pattern. So, if we consider, just looking back here, our first term talked about our term number there to the 0. So we're going to have 8 combinations. 0 was the first, so if I want the fifth term, this would be a 4 then. Okay? And then we would write our 3x and then our negative y in here. Now I need these exponents up here. Thinking about back here, when I went back to every one of these problems, whatever number was right here matched up with that second part. The 3 matched 3, 4 matched that second part. So that means I want to put a 4 here, and then remember these two had to add together to be the 8, so this would also be a 4. So what I would do now is I would just basically come to my calculator. I would take 8 combination 4, multiply by 3 to the 4th power, and then I would multiply by a negative 1 to the 4th, which is a positive, so I'm actually going to type that into my calculator. So I see that I have 5,670 x to the 4th, y to the 4th. And then I'm done. That's it. I was able to find this fifth term. Now, once again, this number here is 1 less than the term number. Okay? So whatever that number is, it's 1 less than the term number, and then that number matches up here. So once again, if I'm asked to find the k term, okay, we would take n combination k, and then we'd have part A, part B. This would be my k, and then this would be the n minus k. If we think back here, let me just slide this under here. Do these formulas look pretty familiar, don't they? We have n combination k, n combination x. Notice p to the, b to the x here, or b to the k, and then that n minus k, that n minus, that's this right here. So we see that this really starts relating to that term. Now do realize that the order changed. This matched with the second one, not the first one. So in a binomial probability, it matches with the first one. Otherwise, it matches with the second one. So let's take a look at one more binomial probability. Once again, a nice real-life one because everybody likes to make fun of the weatherman. Okay, so a scientist hopes to launch a weather balloon on one of the next 3 mornings. Okay, so I'm on number 26 if you're following along in our book, page 736. For each morning, there is a 40% chance of suitable weather. What's the probability that there will be at least one morning with suitable weather? Okay, so if we consider what's happening here, okay, we want the next 3 days. Okay, there is a 40% chance each day that they can launch this weather balloon. So, what we have to start looking at is we have to start looking at, well, what do we want? Okay, we want the probability that at least one day will work. Okay, now this at least one day really is kind of hard to understand fully what's going on, but it's not the worst. So remember, if we want at least one day, we could have the probability of one day or 2 days, or 3 days. Once again, 1 or 2 or 3. So we can start considering that we have an or statement in here. We want to find what's the probability of 1 day. Okay, so once again, we have a combination. Either the first day is going to be suitable, the second day is going to be suitable, or the third day is going to be suitable, all within stating this 1 day. If we talk about 2 days, we could have the first or third, and or the first or second, or the second or third, and then this would have all 3 days suitable. Now we want the probability for that at least 1 day is. Now as we move along in statistics, we would look at this a little bit differently. That would be a little more easy, but that's what this one's starting to get at. So if we want the probability that 1 day would be, okay, we have 3 days we're looking at, and we have a different combination of that 1 day that it could be. Now, we have a 40% chance that it's going to be suitable, leaving us a 60% chance that it's not suitable. And once again, we got 2 of those days that's here. Plus, then now if we look at 2 days, we could have 3 combination 2. We have a different combinations of how we can have 2 days that would be suitable here. Once again, 40% chance that 2 of these days then would be suitable, 60% that 1 would not be suitable. And then 3 combination 3, we'd have 0.4 then cubed, and then 0.6 to the 0 power on here. If we were to multiply, do all our conversions out, we add all this together, we get a 0.784. Okay, so that means there is basically a 78.4% chance that one of the next 3 days is going to be suitable for them to launch. So that means if the first day doesn't work, well, maybe the second day will work. Maybe the third day, there's a 78% chance that they're going to be able to launch this weather balloon. Okay? If we think about this, the first day might be perfect, so they launch it. The second day might still be perfect, but they already launched it, or maybe they got to wait. That's what this really starts relating into and starts relating towards. Once again, we talk about a fixed number of trials. We talk about we have 3 days, 40% chance for each day that we can do this, and then we start looking at the different combinations of things can happen in there. And that's where this is. Now, the complement property would have been tremendously easier on this. We wanted to figure out one probability, but we haven't talked so much about that, so that's why I did it this way.